today to present Professor Mohammed Hajj. He is the Biomedical Professor of Engineering at the Department of Biomedical Engineering and Mechanics, Virginia Tech. He's a graduate of the University of Texas, Austin, and has been Professor at Virginia Tech for almost 25 years.
Thank you, Gina. Thank you. It's a pleasure to be here to talk to you. I thank you for the invitation. Thank you for your attendance. My name is Mohammed Hajj. I'm the J. Bryon Professor of Engineering at Virginia Tech. I'm also the Director for the Center for Energy Harvesting Materials and Systems. Actually, I gave up this position 2 days ago, just to be accurate here, because I'm leaving Virginia Tech in July for another university. So I gave up that position. I'm also the Associate Dean of the Graduate School. I haven't given up that position, but I gave it up in July. And I've been at Virginia Tech as around 8 months, and for the past 25 years. It has been a great experience for me being at Virginia Tech, working with a lot of good colleagues and students, staff, and so on. Let me go ahead and give you a little bit an idea about my research background. And I'm trying to get a message here about my research background because at the graduate school, I work on what's called the transformative graduate education that Dean DePaul has initiated about 10 years ago, or more, 15 years ago actually. So it deals a lot with professional development. And I just want to give you an idea here about professional development and how it works. So I started my PhD. I worked on hydrodynamic stability. The stability of mixing layers, free shear layers. And I learned about turbulence and so on. What I did, nonlinear identification of the transition to turbulence of a free shear layer. So, and then I moved to Virginia Tech, did some of the same things I did with collaboration with Professor Nafi on ship hydrodynamics, worked on ship hydrodynamics and worked on structural dynamics. Beyond that, I used my knowledge on turbulence to work on wind loads on structures. So at the same time, knowing this stuff of nonlinear dynamics, a colleague of mine invited me to spend some time with him at NASA to work on nonlinear dynamics or nonlinear aeroelasticity and fluid structure interactions. So I started learning about aeroelasticity, I think, around the year 2000. I didn't know much about aeroelasticity, but I ended up working on transonic flutter. I ended up working on, aircraft, high-speed transport aircraft, and I ended up working on micro-air vehicles. And all of this came together through, basic knowledge in nonlinear dynamics transferred into new fields and so on. So then I used the knowledge in structural dynamics and knowledge in nonlinear dynamics and fluid structure interactions to do energy harvesting. So basically, when you're designing a wing or you're designing an aircraft, you want to avoid aeroelasticity. You want to avoid flutter. Energy harvesting, you want flutter to happen. So, I used the same knowledge from one field to the other field. I transferred what I wanted to prevent it here. We want it to happen here. So use the same knowledge, but suddenly I'm working in a new field, which is energy harvesting, vibration-based energy harvesting, fluidic power energy harvesting, and thermoelectric energy harvesting. So the message on all of this that I want to get is that if you go out to work in industry later on, you realize that every 3-4 years, you might end up changing your job. In academia, it's almost the same thing. Even though I stayed for 25 years at Virginia Tech, every 3, 4, 5 years, I had to do something new. I had to learn about something new and work on it. And I have to say that I couldn't have done this by myself. I did this in collaboration. The students who supported me, the staff who supported me, my colleagues. I had great colleagues. The agencies that supported the research and so on, and the industries later on through the center were very important component of it. So when I speak, I'm not speaking about what I do. I'm speaking about what I could do when I worked with others. Okay, and that's very important also in my professional development as a story. I'm going to give a couple of examples before I start talking about identification of nonlinear piezoelectric coefficients, and just to tell you the extent of what we do in the research group. So one of the things we do through the support of the center is wirelessly controlled harvester and sensor system. And what we did here, we take this microturbine here, and we generate some power from it. And water passes through it, it turns, it generates some power. And we're going to use this as a harvester to harvest energy. But we also would like to use it as a sensor, okay? Because the amount of energy it harvests also depends on the sensing capability. But we cannot use it at the same time as a harvester and sensor. We want to be able to control it wirelessly, harvest energy over a period of time, let it go, charge a battery, then at some point stop the harvesting and say, okay, now we want you to sense the flow, okay, using the same device. Why do we want to use the same device? Because it's important when we think about energy harvesting and sensing devices that we're going to put thousands of them in any network. Okay, it's important to think about the power density. Power as related to the mass, power related to the volume, okay? I mean, one could put several of these devices or sensing and harvest with one and sense with the other one and connect them together, but sometimes the space is too tight to put two of them, okay? And if I'm going to put thousands of them, I want to reduce the amount of things that could go wrong. So this microturbine is going to be here, our harvester and sensor. At some point, we're going to have a relay switch here. When it is closed, it's going to charge here a battery through a charging module, basically a voltage regulator. It charges the battery. Life is good. Then wirelessly, we're going to open this relay switch here, and we're going to send a signal to a Raspberry Pi here and say to the Raspberry Pi, start taking data of what's going on with this as a sensor. So start taking data through using this data acquisition system. So the idea here is that over some period, it charges the battery. Over another period, it takes data using the power from this battery itself that's being charged. So this is the experimental setup here. And you could see the hydro turbine here, the data acquisition system, the battery, the flow meter, and so on. It's a little bit complex, not complex, but it has many components. But this is just to prove the concept. We could later on do something about putting these components together. And this is here where we have the signal. Over this period, we're charging the battery. Over this period, we're taking flow rate. Then we charge battery, take flow rate, battery, flow rate, and so on. We could repeat this using the same device through that control system that we just generated. Before I talk about this, let me talk about another piece of the work that we're performing. Okay, I'm sorry, I'm going to keep it like this. I couldn't try to include this video in the PowerPoint. Here, we're trying to understand biomimetic or bio-inspired locomotion. So we're going to have a fish body, a fish-like body, and we're going to flap it in the back. And these are tests we do in the wave tank at Virginia Tech. And you could see it moving at a specific speed, and we could measure the torque that's being input. We could measure the displacements. We could measure everything we want to do, and just to be able to assess how we can design some underwater locomotion of a body, of a fish-like body. It's designed in such a way that we could do many modular design and so on. We're looking at different things. We're doing the experiments to validate some of the numerical stuff we're doing. And we're doing something which is also a very interesting concept. As the tail of the body moves at high frequency, it impacts the stability of the body itself. So we're trying to look at the stability of the body as we're flapping the tail in the back. So we're doing the theoretical work, the numerical work, as well as the experiments. And this work is done by 2 students that are still at Virginia Tech. Okay. Now we're done with the fun. We're done with the videos, and we're done with the pictures and all of the stuff. Now we're going to do some equations. So I'm going to move on now to some analysis, and I'm going to show some of the things we tried to do. So the rest of this dissertation is actually based on what one of the most recent master's students has done. Vamsi Misala, he's about to graduate. He'll graduate this semester. I wanted to present this here as an idea about what we have done. So there will be a lot of equations. I usually don't talk about a lot of equations, but I think it's interesting to see things as we talk about them here. Okay, so we're going to take a beam tip mass system, and we're going to do some analysis on it. We're going to do some modeling first. We're going to do some analysis, and we're going to try and figure out some of the things that are probably some good ideas. The first thing is sensitivity to addition of a little bit of mass, or sensitivity to the fatigue of the beam, of the response. And then we're going to look at identification of the nonlinear piezoelectric coefficients. So let me start here by, this is the beam with the tip mass in here. And we apply Euler-Bernoulli assumption. The beam is thin, and the rotational effects can be neglected, and very high aspect ratio. The beam is also assumed to be inextensible. To derive the governing equation, we apply Hamilton's principle. We take the variation in the kinetic energy, in the potential energy, and virtual work, and we make it all equal to 0. So this is the potential energy, this is the kinetic energy, and this is the virtual work in here. And in this case, we're going to look at the parametric excitation. Later on, we'll look at the direct excitation. So we're exciting the beam in the vertical direction here, and the response is at half the frequency in the horizontal direction. Oops. So this is the mathematical model. Once we set up Hamilton's principle and we do all the analysis, we end up, or all the mathematics, we end up with these governing equations in here. And this governing equation has the following essential boundary conditions. That is at x at the fixed end, and we have the natural boundary conditions at the free end. And the natural boundary conditions we have in here, these terms that appear in here, these are the linear terms. These are here the nonlinear terms that are a part of this boundary condition. So sometimes you linearize the equations and you get rid of these terms in here. We want to see what is the effect of getting rid of the nonlinear terms in the boundary condition at the natural boundary condition. Oops, I should do this. So how do we solve this problem? We're going to solve it 2 ways. We're going to solve the whole problem basically through a direct approach. We're going to implement the method of multiple scales on the governing equation and boundary conditions and solve everything together. Professor Neff used to say we attack it using the direct approach. Okay? That's how we're going to solve the problem. And then we're going to discretize it and solve it. And we'll just see how the discretization, what it takes care, and so on. So here we're solving the, oops. We're going to use the method of multiple scales. In the method of multiple scales, you're going to take different scales. You're going to divide the time into different scales. You're going to slow scales and fast scales. And these are defined by the epsilon here, some kind of a perturbation parameters. And then once we do that, we're going to put all the derivatives in the equation in terms of these. Instead of d small t, we have now d dt0, d dt1, d dt2, and so on, and d squared, dt0 squared. And we have all of these terms in here for all the derivatives. And with mathematical, life has become so simple. You could put these things, even if you don't know them very well, it works out, I guess. It should. So if you do it right. Then what we say is that the solution is actually we get is not an exact solution. We get an approximate solution. So the displacement now is W0 plus epsilon W1 plus epsilon squared W2 plus so on. But because epsilon is small, so we could stop at some point and say the rest of these terms are not really important. So when we put this, when we put this solution and these derivatives into the original equations, we end up with terms that have epsilon to the power 0, terms epsilon to the power 1, terms epsilon to the power 2, and so on in the equation. Okay, so because of the way the equations look now, terms that are to the power epsilon 0 must be equal to each other. Terms that are to the power epsilon 1 must be equal to each other, and so on. And you could expand this, quite a bit. But usually you don't need to expand it that far. You could expand it up to a certain point, and then it works out fine. So one of the outputs, okay, so in this term, in this equation here, you end up with the linear undamped forced equations in here with the boundary conditions. So for epsilon 0 as an example here, and then you take this solution and project it on the first mode as the forcing doesn't excite other modes. So what we're saying here is that even though I'm solving the direct problem, when I'm exciting it, I'm going to only see the response at the first mode, because all the other modes are going to die, because I'm exciting it so that that mode appears. That is what we're saying in here. So we do this, and we do what's called solvability condition. We end up in here with what we call the modulation equations. These modulation equations, giving them in this form in here, this D is not a power. This D is just meaning direct approach in here. So basically, this is how the amplitude of the first mode varies, and the gamma here is how the phase varies in here. So, okay. Okay, just remember these modulation equations. Next, we're going to discretize it, and we're going to do a Galerkin discretization. We're going to assume, that the solution is a product actually of the mode shapes with the temporal functions. Okay, and we're going to just put them in, and we're going to say we're going to look only at the response of the first mode. So we do it with the direct approach, and we do it with the discretization. Now, when we do the discretization, with the linear boundary conditions, this is what we get in here for these delta L, alpha L, and eta L. Delta L here is a coefficient of both delta L and alpha L are like nonlinear coefficients. But what we have in here is the representation in terms of the mode shapes, the mass, and the physical parameters or material properties of the beam, the E and the IY, phi prime, M mass, and phi, and so on. So that's how we can represent delta L. And this is important for us if we're trying to do any identification of the problem, to see how delta L and how alpha L, what they are. And we call them delta L and alpha L because they're linear. Now, what happens if we take nonlinear boundary conditions? We have a different representation of delta and alpha and eta L. Okay? And that is because some of the terms actually go away when we do the nonlinear boundary conditions. That is important to realize, because if I'm trying to study this problem, if I have different delta L's and alpha L's, whether I have linear or nonlinear boundary conditions, my whole system is going to respond differently. Isn't that right? Because the nonlinear parameters cannot be different. There is only one nonlinear. There is only one parameter. That parameter is defined by the experiment that I'm doing. So when I linearize them, I get different coefficients, different nonlinear coefficients, and that's not good. But anyway, it turns out actually, as I said, the nonlinear boundary conditions gives us a more simple representation of the boundary conditions. So we take these equations, we apply the method of multiple scales, we end up with these following modulation equations here when we assume nonlinear approach. And if we take cosine square gamma plus sine square gamma equal 1, we end up in here with the steady state amplitude response relation. This amplitude response relation is the same one we got from the direct approach when we did the direct approach. So just to give you an idea about what happens if we assume linear boundary conditions instead of nonlinear boundary conditions, actually something big happens. That, this is here, if we have detuning, positive detuning, with the linear boundary condition, you get some kind of subcritical bifurcation. With the nonlinear boundary condition, you get a supercritical bifurcation with the linear boundary condition, subcritical bifurcation with the nonlinear boundary condition. And that's a big difference to get subcritical or supercritical boundary condition, okay? The same thing here, if we have negative detuning, we get actually a subcritical response, a supercritical response, a subcritical response instead of a supercritical response. The linear one is the dashed one, so this one is the accurate one. So we get subcritical instead of supercritical. Here we get supercritical instead of subcritical. So that tells you the importance of these things. And that comes simply because these delta L's and alpha L's are different in this problem when I linearized the equations. And the reason we want to say this is because in many applications, when we think, okay, linearize the boundary conditions and don't worry about the rest of it. And as it turns out, actually, if you linearize the boundary conditions, you could impact the physics of the problem pretty badly. Okay. Now that we know this about it, let's see if we can use this for sensitivity analysis. There are many ways to do sensitivity analysis that people can do it. And I think one important thing is, how can I do sensitivity analysis that lets me across a bifurcation, across a singularity? That's important. Sensitivity analysis, you go and you take a parameter and you say, I'm going to change it by a little bit. What happens to the response? And you could take the variation of the response relative to the variation of the parameter, and you say that is the sensitivity. But if you have a bifurcation, that's like a singularity. The whole system is changing. Isn't that right? So how can I figure that one out? Okay, so a lot of tools that are there for uncertainty quantification and sensitivity analysis cannot predict this type of bifurcation, what happens if the physics of the system change. So we're going to do, again, multiple scales here and try to see what happens in the sensitivity analysis. And this would be important for things like MEMS applications, where you're trying to detect like small variation in the mass at the tip, or where if you have a wing in here and you have a store and you release the store, the whole thing changes in the wing. I mean, what happens at that point. So things like this. There are many other applications. The other one, we want to look at fatigue induced by cyclic loading. So you take any system and you do a lot of cyclic loading on it, and it changes, so what happens to it? Or manufacturer tolerances. You design these things, the E varies a little bit or something, or the I varies the thickness, or the width of the beam varies a little bit. So what happens in here? So we're going to take our system, we're going to assume that the E is changing here, and this is epsilon sigma E. This is the variation in the modulus of elasticity in here, and this is alpha. Remember, that was our alpha. So the E changes. Because of the change in E, we assume everything else, Iy stays the same. So alpha prime is equal alpha plus E1 plus epsilon sigma. Here, omega is square root of E. So omega prime square is omega squared 1 plus epsilon sigma. Okay, then we have now the governing equation. And now we have here epsilon del Q, but the alpha prime in here has another epsilon in it. So we have now an epsilon square. So we have to solve the problem up to the order of epsilon square in order to see the impact or to detect the sensitivity, which is, again, what we're going to do. So these are the responses when you solve them. Okay, so one of the things we want to say, okay, if I solve the original problem without any sensitivity analysis to the order epsilon, epsilon square, how much difference do I see? Because we want to establish that one also. There is a little bit of difference here that you see it, but we get closer to the actual solution, and as we move further away from the bifurcation point, because multiple scales gives us everything around here very well. But as you move away from the bifurcation point, you need to add those other approximations into the solution in order to get them. So this is again what we get for positive detuning, for negative detuning, for order epsilon, epsilon squared. So the epsilon square actually gets us closer to the solution. So now we're going to solve this problem in here. These are the parameters, choose many parameters. And this is the one here, epsilon sigma e, where we don't have any variation. And then we're going to say the modulus is being reduced due to fatigue. As we reduce it due to fatigue, the modulus is being reduced and in here. And this is the case of a negative detuning. So this is the response as it should be. Once it is reduced by 0.167%, a very small reduction, one could actually get this response in here. So instead of a supercritical bifurcation, you get a subcritical bifurcation. So what we're saying here is that I could take my system, or I could take, for now, the beam and tip mass, and I could excite it, and I could look at its response. And every time it's supercritical, life is good. But if it is fatigued too much, when it changes, the E changes by a little bit, then I'll see a subcritical response. So now I could use this in a way to identify how much fatigue I'm getting in the system if I wanted to, even if it is a small amount. And that's a big change. I could see it. Instead of trying to look at a derivative of a small function or of a continuous function, now I'm seeing a big change that I could detect it very well. We do the case in here for positive detuning, again, in here. And you could see that initially we would, this is for the mass in here. We're changing the mass, radial mass. So initially it has a supercritical response. As some mass gets added, 0.2%, you end up having a subcritical response in here. And we did the analysis of the detuning effect of the frequency change and so on is all included in there. So again, a small addition on the tip mass gives me actually a way of detecting it through sensing the change in the type of the bifurcation. I can detect. So if I have a beam, I'm exciting it always in a supercritical fashion, expectation response supercritical fashion. I know no mass is there. I'm exciting it. It responds in a subcritical fashion. I know some mass must have gotten bonded to the tip mass or somewhere. And now I have a better way of doing this sensitivity to the variation of the modulus and mass. Okay, these are here. Now, those differences, how close I want to be to detect these masses, can be controlled by detecting the initial detuning. So, if I change the detuning here, I could detect, over larger changes or smaller changes, depending on what I want. So I could look at it from the initial detuning of the system. Now, let's talk about identification of nonlinear piezoelectric coefficients. I'm not a piezoelectricity expert. I just know you put strain, you get voltage, you put voltage, you get strain, something like this. But a lot of people, when they talk about nonlinear effects in piezoelectric, they're trying to say, can I exploit nonlinear effects in order to do things differently with the piezoelectric? Like get a broadband, energy harvesting over a large broadband, and so on. And really, we haven't seen much on trying to identify the nonlinear piezoelectric coefficients. These are piezoelectric coefficients are important. This is energy harvesting from a shoe. It has a piezoelectric element in it. This is a project that we started to work on actually recently with Dr. Shahab in the department, which is wireless power transfer through acoustic waves. So So we have a piezoelectric element here, a piezoelectric element here. This one generates a piezoelectric, an ultrasound wave. This one receives it, it starts vibrating. We pick up the energy here from this one. It has many applications, you know, if you want to charge a pacemaker in a body or if you want to charge any element. And the neat thing we're working on actually is that you could do it localized. Like you could send your acoustic waves in different ways to power different things at the same time. So this is a project that got funded last year by NSF, and we're working on it. Of course, piezoelectricity is used also for control and for energy harvesting in these other applications. One of the things is the work by von Wagner and Professor Hagedorn, who, when they were looking at the amplitude response function of this cantilever beam experiment here with a bimorph, they saw a softening effect. And then they defined the nonlinear, they defined the enthalpy that led to this softening effect. So we're going to work on this problem the same way we did the parametric problem, but we're going to do it here under direct excitation. And we're going to say, let's exploit a specific behavior in order to get these nonlinear piezoelectric coefficients. We're going to exploit a specific behavior. And this is something I learned from Professor Nafi again, where, you know, say, I have a system, it's going to respond in this way because of one parameter. It's going to respond in a different way because of a different parameter. So why don't I make it respond in this way, figure out this parameter, make it respond in a different way, figure it out this parameter, and so on. And I could repeat this for as many parameters as that are important in the system. So this is the beam with the tip mass under direct excitation in here. We add the piezoelectric element. And again, we define here that we have Hamilton's principle here with the kinetic, potential, and virtual work variations. And all we have to do now, this is the kinetic energy everybody familiar with. This is the virtual work in here. And now we have this expression here for the potential energy that includes the strains as well as the strain and electric field relations. And those are the regular modulus of elasticity here for the substrate and the piezoelectric and so on. And E is the electric field in here. And you could see all of these coefficients, alpha 1, alpha 2, alpha 3, alpha 1, alpha 2, alpha 3. They are representative, alpha 2, alpha 3 rather, they are representative of the nonlinear piezoelectric coefficients. Okay? So now we derive the equations, and again, we do the discretization. We end up with these governing equations here. These are coupled. We have here the voltage generated, and we have here the equations governing the voltage. And these are the different parameters that we have in here, delta 1, delta 2, delta 3, as a function of alpha 1, alpha 3, and alpha 4. And we have all of these parameters, and in here somewhere there should be alpha 2 too. Okay? So now if I can run an equation, if I can run a simulation or an experiment, okay, I can identify all of these terms because I have a representation for delta 1, delta 2. If I get delta 1, delta 2, delta 3, and delta 4, I could determine all of these coefficients. Okay? So if we do the analysis, we're going to end up with an approximate solution. This is the approximate solution, but written here in the Fourier domain. Okay? Nu here is the frequency, and S is the position along the beam. Okay, so here we have this, and you could see response at the frequency equal to the excitation, frequency because it's a direct excitation, frequency equal twice the excitation, here the DC component, and this is the voltage in here. And you could see that this term here depends on delta 1, this term here depends on delta 2, and I'll go one more, let me go now. Here, and you could see that if I look at the steady state amplitude response function, I have delta 3 in here somewhere. There it is, delta 3. So I run the experiment, or I run the numerical simulation. We're going to do numerical simulation. And then from the mean value in here, or from the DC component, I can get delta 1 from this A0, which is in here, I'm going to be able to go get delta 1. Delta 1 is related to alpha 1, from which I can get alpha 1. In here, I can go and get the second component. I can get here, I have delta 1, I can get delta 2. And then from the steady state amplitude response relation, which is shown here, I could get this delta 3, knowing delta 1 and delta 2. They should be somewhere in here. And everything else. So delta 3 is related to alpha 4. So I'm being able to get alpha 1, alpha 3, and alpha 4 from this analysis for the nonlinear piezoelectric coefficients. So this is the example that we show in here. And we put all of these terms, and we did all the analysis. And these are the values we figure out for alpha 1, alpha 3, and alpha 4. And that is how we identify them. From this value, we get delta 1. From this value, we get delta 2. And we get delta 3 from the amplitude response value here. So this is the value alpha 1 as we put it in. These are the estimated values. And you could see 10 here, percent error, 4.4, and 3% error. So we could estimate them back to within a small error. I have to say here that it was a very big challenge to be able to estimate all of them at the same time to this error, because it is impacted a lot by the detuning parameter. Some of these values change quite a bit with the detuning parameter. So one would need to do many detuning, many experiments with different detuning parameters in order to be able to converge on the good value if we are doing it with experimentally. But here, because we know them, we figured them out. But in an experiment, which we haven't done yet, what we would like to do is do many experiments at different detuning parameters to be able to see how close we're getting, how we're converging to a specific value. And with that, I thank you very much. Thanks.
Open the floor for questions. I'll have the first one. I'm Josh. So, why should we do this?
Why do you want to do?
Meaning, I suspect a lot of people are thinking, well, and they can get it out of the table. Parameters. Because I have seen a paper somewhere that lists the piezoelectric coupling coefficient, V31 and G31 and stuff.
I think those are the linear ones.
Yes.
I don't think many of them list the nonlinear ones. Do they
Not
list
anywhere.
Not anywhere. Yeah, I don't think many of them list the nonlinear ones. The linear ones are easy to get. Yeah. So that's why. Did I answer your question?
Yes.
Okay.
I'm suspecting that some would have this question. This is a lot of scary math. Why should we go there?
Well, actually, you don't. The math might be scary. It was much scarier during our days because we didn't have Mathematica.
You have to do it by hand.
When we had to do it by hand. So now with Mathematica, it's really not that bad. Okay, I think defining the strategy is really the tougher part. Is how you want to get these parameters and how you do the estimation.
The critical issue is you couldn't find these in a book or a paper.
Yeah. Yeah.
So you'd have to, if you want to do this, you'd have to do the parameter ID first.
Yeah, and I could add one more thing here, is that people are always developing new variations of piezoelectric materials. Mm-hmm. You add things to them and you expect them to respond in a certain way. You put them on, different substrate and so on, and how do you get all of these variations? Because they respond differently if you have them on different substrate.
Even the traditional ones like PZT, the parameters are not listed.
Yeah. So if
they have been beating on PZTs since the 70s.
Yeah, exactly. So if you have a way to estimate these things with different substrates and different response and so on, it'll help. Because that depends also on the epsilon, on the strains that you can induce in the substrate. And so on. Yeah.
Any more questions? I have another one.
Okay.
So I didn't catch the difference between the linear and the nonlinear boundary conditions. It went too fast for me.
These are the linear boundary conditions. For what? Okay, I'm sorry.
Statement.
Yeah. Okay, so when we do the linear boundary conditions, delta L and alpha L are these representations. When you do the nonlinear boundary conditions, as it turned out, some of these terms add to zero, disappear,
Which is elegant.
which is very elegant. Some of the terms in the governing equations disappear.
So what is the physical difference between the linear and the nonlinear boundary conditions? Or what is it missing in the linear boundary conditions?
What?
That's my question. So what would the nonlinear boundary condition look like?
So these are the linear boundary conditions will be W3 prime minus M W dot is at S equal to 0.
Yes.
And these are the nonlinear boundary conditions. It's missing these, all of these other terms. As it turns out, actually, the Rayleigh-Ritz equation is fine because you assume the mode shape and it works out fine. But we wanted to understand it a little bit more. But what you're missing are these other terms here.
So this is in the shear boundary condition.
Yeah, that's right.
The shear boundary condition.
The shear boundary condition. That's right.
Okay.
Yeah.
Go ahead.
Not a piezoelectric expert. So
Neither am I.
Basic. But does a piezoelectric material act similar to, let's say, a magnetic generator where you always have to turn the magnetic coil to generate current? So when you have piezoelectric, you introduce deformation, it provides voltage. Do you then have to release it and again deform it for it to provide voltage? Or when it's deformed, then it provides voltage at all times?
No, it has to vibrate
Okay.
in order, yes.
Alternating.
Yeah, it has to vibrate to provide
Then,
voltage.
second question, which is also basic. How would you go from the piezoelectric coefficient to the power output of the material, let's say, per square meter? Because
How do you go from the piezoelectric coefficient to the power output? Okay, so let's say this is the simplified beam mass system. And you can see I'm exciting in here. Okay, and one would expect that I excited higher. Okay, a couple of things. I excited higher, I get more power. Higher amplitude, I get more power. But at some point, nonlinearities kick in. And what nonlinearities do, they take whatever power is coming in at that frequency and start redistributing it to other frequencies. That's what the nonlinearity is going to do to you. Okay? So you start getting, if you want, broadband energy harvesting or some, you could, now you could get actually the nonlinearity, what it will let you do also, you could excite it at frequency different than resonance and get energy out of it. So that's what the nonlinearities do to your system. Did I answer it? What?
just how would you actually calculate, let's say, if I deform the material by some amount,
Oh,
then I'm going to provide.
so you see this equation here? This Q is representative of the displacement. The displacement associated with the first mode of the beam. And you see this V here is the voltage that's being generated. So you see this second equation here is the electric equation. Here you have the voltage also related to Q. So you have these two equations that are coupled. So you change Q, V changes. Okay? You change V, Q changes. So these are a system of equations that are coupled. So that's how you can calculate them.
And when you solve it, you have to transition with linear and nonlinear coefficients.
Oh, you could solve this equation in here by saying, you see here, let's say this delta 2 term here depends on alpha 3. Okay, I'm going to only do linear term. So this term here, which has delta 2, goes away because that term is the nonlinear part. Okay? Which other term here? This other term, delta 3 here, depends on alpha 4. So the alpha 4 that I had in the original equation goes away if I get rid of it, or part of it goes away. You follow me?
Yeah.
These are the nonlinear terms. You see, when you take Q multiplied times Q, that's a nonlinear term. When you take Q multiplied times V, that's a nonlinear term. When you take Q multiplied times Q dot, that's a nonlinear term. Those are the nonlinearities. You could say a lot of people actually, if you go to the literature, you're not going to find this term in here because this is a nonlinear term. They don't look at it. We have many papers where we don't have this term because we assume that piezoelectric nonlinear coefficients are not impacting the response. Well, I mean, they do if you increase the amplitude or under different excitation conditions. Make sense? You have a question?
You find nonlinearities in piezoelectrics to be alpha 1, alpha 2, and alpha 3, the coefficients. Are these strain nonlinearities or are these electrical nonlinearities? Meaning,
Yeah. So let's look at them in here. So epsilon here is the strain. So alpha 1 is related to the strain nonlinearity. Here you have epsilon 1 cubed E3. So this one is like nonlinearity between the strain and the piezoelectric. And this one here is also nonlinearity between the strain and the electric field.
but they're all first order in the electric field.
Yes. Yes.
No, you have a quadratic term electric field.
The E3 squared,
Yeah.
epsilon 3, yeah. Okay, we have this quadratic term.
Coefficient.
I have to go back and, yeah. Okay, I don't have the full thing. There is no coefficient here. What, epsilon 3s. Yeah, it's just a quadratic term in the electric field.
So I'm
And-
asking basically if you included the electrostatic.
No, no. I think it is a linear.
This is the potential field, so this is
That's right, it is a linear. Okay. Somebody had a question back there?
admit to the question.
Huh?
Admit to the question.
Admit to the question. Okay.
Now, underlying this, there is a scaling assumption about the scale of the piezoelectric of the potential energy in the strains to the potential energy in the electrostatic field, right? So you assume,
Okay.
so you're assuming that the intensity of the strain energy is higher than the intensity of the electrostatic field.
That's right. Is that a bad assumption?
No,
Okay.
it works, but you could also do
The
tricks and reconfigure the system so that the intensity of energy stored in the electrostatic field is higher than that
The
in the strain, and then it will change the linearities and
I see.
produce a different system.
Okay. That sounds like a plan. If you have an electrostatic field.
Yeah, sounds like a problem I'm stuck in.
Okay.
Any further questions? Then let's thank our speaker.
Thank you.
Thank you.